Hey, this is Stefan Roman, and in this module we'll look at backup and recovery solutions that DynamoDB offers. In particular, we'll look at on-demand backups and point-in-time recovery options, where we'll go through their various features. We'll learn what happens when on-demand recovery is initiated, as well as we'll learn about how point-in-time recovery works. We'll also learn about what on-demand backs up and what it does not, as well as what both of the solutions recover. We'll log into the Amazon console and create a simple table, store a few items within it, create on-demand backup and create a new table from the backup. During the demo, we'll also observe DynamoDB settings which are not being restored from the main table. We'll also enable point-in-time recovery option, delete and update few items and recover them using point-in-time recovery feature. So what is on-demand backup? It allows us to create full backups of tables for long-term retentions or archival for regulatory compliance needs. These backups are preserved regardless of table deletion. It's possible to create backup anytime without performance or availability impact. We can create backups in seconds regardless of table size across multiple partitions with no scheduled or long-running backup processes. On-demand backups come with no additional pricing except pricing associated with backup storage size. So how does it work? Let's say that Emma creates a backup of her table. The backup gets created at no additional cost. However, there are charges for storage capacity this backup will consume. Because an entire table is backed up, the price for storage depends on the amount of storage the base table consumes. Now let's say that Emma wants to restore this backup. What happens is that when a backup is restored, a new DynamoDB table gets created. The table will have all backup data contained within it. What is backed up exactly? Also, what settings are restored when we restored from backup? Local and global secondary indices are backed up and restored also. DynamoDB streams, provision read and write capacity is also backed up and restored. So what does not get backed up and restored? Auto-scaling policies. So when we restore provision capacity stays, however the actual policy will not be restored. Access policies, CloudWatch metrics and alarms, DynamoDB stream settings, and time to live settings. We have to manually restore these settings to restore tables every time. In the following demo, we'll create a simple DynamoDB table with provision throughput as well as auto-scaling policy. We'll store a few items within the table and create a backup. We'll then restore the backup, which will create another table. We'll observe which configuration was applied and which was not. We'll also take a look at whether stored items are present. Now that we are logged into the console, let's create our table. If you remember, we defined what settings should and should not be transferred to table created from backup. We can therefore apply auto-scaling policy at this stage which should not be transferred. So let's click on Create Table. Let's name this table On-Demand Backup Table. Its partition key name can be set to name and sort key can be set to age. Let's not use default settings and apply provision capacity auto-scaling. Let's say we want 3 read and 3 write capacity units at minimum and 8 at maximum. This setting will not matter very much as it won't be transferred to our new table restored from backup. Let's also add local secondary index as these can only be created when creating the table. Partition key name has to be the same as in base table, so we write name. Add another sort key and call it time. We don't really care about these attribute names this time, so we can name them whatever we want. Let's click Create as local secondary index and name it LSI. We can add a global secondary index also. Let's add a partition key position and sort key company. And let's call it GSI. Let's create this table and wait until it provisions. Let's add a few more features and see whether they get replicated to our recovery table. Let's turn on TTL attribute and streams. We can call our TTL attribute expire. Now we can store a couple of items within the table. Let's copy and paste a couple of items here to text editor. Now we are ready to create our backup. Let's go to Backups tab. Click Create Backup. Choose our table, On-Demand Backup table, and name this backup Table Backup. Click Create, which will create our backup here. We can see that the backup was successful. We can now create our recovery table. In Backups tab, click on Table Backup and then Restore Backup. We can see all the settings that will apply to our new table, as well as both secondary indices. We can name this table On-Demand Recovery Table. Let's create it. Click on Restore Table. This process might take some time, even though we haven't consumed a lot of storage. Now the recovery table is finally provisioned, we can have a look at what settings were kept. As expected, we can see that the auto-scaling policy was not transferred to our recovery table. We can see that the provisioned read and write capacity units at the time of creating the backup were kept, but the policy itself was not. We can also see that streams and TTL settings were not transferred over either. Let's have a look at our indices. We set the name of these indices to LSI and GSI, and here they both are. Let's have a look at our items. There should be two, one with partition key Jane and the other Peter. And surely, here they both are. So what is point-in-time recovery? It's DynamoDB feature that protects tables from accidental write or delete operations. Point-in-time recovery reduces the need to schedule or maintain periodic backup solution or even use DynamoDB on-demand backups. Point-in-time backups are available for 35 days. This value cannot be changed to more or less days. After point-in-time recovery option is enabled, we can restore to any point in time between the time the feature is enabled and 5 minutes from current time. Let's take a look at the following example. Let's say that we create a table without point-in-time recovery feature here. We enable point-in-time recovery later on, here. Now this point in time becomes what AWS calls the earliest restorable date time. After a few days we make a mistake and remove an item which was not supposed to be deleted. And we want to recover it. However, we can only recover 5 minutes away from the present time. This is what AWS calls latest restorable date time. The range between the earliest and the latest restorable date time is 35 days at maximum. So anything older than earliest restorable date time is lost forever. Similarly to on-demand recovery, with point-in-time recovery, a new table is created when we recover to point-in-time. So what settings are restored? Local and global secondary indices, provision read and write throughput capacity, and encryption settings. Again, very similar to on-demand's backup, what is not restored is auto-scaling policies, access policies, CloudWatch metrics and alarms, stream settings, time to live settings, and also point-in-time recovery settings are not restored, so again we have to apply them manually every time we recover a table. One major difference in use case for each backup solution is that on-demand backups are generally considered to be implemented for compliance purposes. Let's say when a company requires to keep a year worth of data. In that case, they can use on-demand backup feature alongside the script which will create a backup every day for a year and then delete all the backups. When it comes to point-in-time recovery feature, it is more tailored towards disaster recovery. As I mentioned, we can use it in cases when an unwanted deletion or modification takes place. But we have to keep in mind that we can use point-in-time recovery option for compliance purposes also if data retention policy is 35 days or below. It really depends on the use case and company requirements and policies. In the following demo, we'll enable point-in-time recovery feature to the table from previous demo. We'll delete an item from previous demo and modify the other. And using the feature, we'll go back in time and recover the items. Let's select our on-demand backup table. Click on Backups and then enable point-in-time recovery. It'll give us a warning about additional pricing. This is the pricing related to additional storage consumption. Click Enable and wait a few seconds. We can see the earliest and latest restored dates now. Let's take note of the time here. It's 1:50 p.m. After we modify our items, we'll try to restore them as they appear on this time. Let's go to Items now. We can now delete item with partition key Peter. Then we can modify item Jane. Instead of her position in HR, we'll modify it to gibberish. Click on the item and choose Edit from the Actions menu. We'll also add another item to the table here. This is so that we can see whether it'll appear in our recovered table. Now we are ready to restore our items. Go to Backups tab again and click on Restore to Point in Time. We can call a new table Point in Time Recovery Table. We also have to set the time to when our items were untouched. The time was 1:50 p.m. and this time is correct. Let's click on Restore Table. We'll have to wait a few minutes for it to provision. Our table is provisioned now. Let's check out the state of our items. And here we are. Item with partition key Peter is back, and item with partition key Jane has its position set back to HR. So that's it for this module. To summarize, in this module we went through backing up and recovering DynamoDB tables using on-demand backup solution as well as point-in-time recovery solution. We learned that when recovering from either on-demand backups or going back to point-in-time, we lose some of our DynamoDB settings. We also learned about use cases for each solution where on-demand backups are more tailored towards compliance purposes and point-in-time solution more towards disaster recovery. We also learned that backing up a table is a fast process with no downtime or availability degradation. We also logged into the console, created a table with few custom settings, and observed the restoration of items to point in time, as well as recovery from on-demand backup. We'll look at monitoring DynamoDB tables with CloudWatch. Before we start looking at specifics, we're going to learn about monitoring concepts. For instance, what are we trying to accomplish with monitoring? We'll also learn about common monitoring problems and how to look for them and how to remediate them. Then we'll look at specific DynamoDB metrics. We'll briefly go through each important metric. Then we'll set up active monitoring for our elaborate employee table using CloudWatch alarms as well as CloudWatch events. At the end, we'll learn how to create CloudWatch dashboards. During this module, we'll also use a script to produce random traffic to our tables so that we can experience realistic monitoring scenarios. Before we start creating complex monitoring solutions, we need to take a step back and answer a few simple questions. Answering these questions Hey, this is Stefan Roman, and in this module we'll look at monitoring DynamoDB tables with CloudWatch. Before we start looking at specifics, we're going to learn about monitoring concepts. For instance, what are we trying to accomplish with monitoring? We'll also learn about common monitoring problems and how to look for them and how to remediate them. Then we'll look at specific DynamoDB metrics. We'll briefly go through each important metric. Then we'll set up active monitoring for our elaborate employee table using CloudWatch alarms as well as CloudWatch events. At the end, we'll learn how to create CloudWatch dashboards. During this module, we'll also use a script to produce random traffic to our tables so that we can experience realistic monitoring scenarios. Answering these questions will make our job easier when it comes to creating alerts, dashboards, or watching logs. The first question being, what are we really trying to accomplish by monitoring our resources? The answer should be simple, right? But the real answer is much more complex. Do we want to monitor our resources' performance? For example, we could create a monitoring solution to monitor specific performance metrics. In DynamoDB world, this could include metrics to monitor capacity autoscaling and throttling. Well, in this case, how do we know at what point the metric is telling us that there is a problem? We could look at trends of a particular table and look at spikes or dips in metrics and correlate this data with, for example, support tickets to see when customers complained about application slowness or unexpected errors. Or do we really want to monitor our resources availability? Is our application up and running 24/7 without any outages? In DynamoDB world, we don't really have control over API's reliability to access particular tables. However, we could in this instance monitor errors that are happening over time. For example, if a bugged application which communicates with our DynamoDB table is deployed, then we could see malformed requests being made to our table and potentially inform our developers of such problems. But what if, for instance, we look at metrics and we see constant errors but no complaints from our customers? We really have to investigate behaviors of our application we are trying to monitor over time, as well as investigate previous complaints and issues that were reported. The next question is, which resources do we really want to monitor? Companies usually have multiple environments deployed, for instance, production and development environments, each serving a different purpose, but each having a different priority in resolving issues that might arise or any alerts which are produced by a monitoring solution. In DynamoDB world, which tables would we want to monitor in production environment? We might not need to monitor all of them, and perhaps some development tables during performance tests. This is really up to our use case and requirements. The next question is, what tools do we want to use? Do we want an active solution where alerts are being produced and sent to notify responsible people? This question is somehow related to what threshold should be set for each metric. During active monitoring, we need to define thresholds for specific metrics. The question is, how do we know what the thresholds are? Or do we want to implement a passive monitoring solution to look back at our trends to see traffic spikes or errors and adjust infrastructure proactively? Last question that we should be asking is, who is the person responsible for a particular alert when it occurs? Who will receive notifications and how? Let's talk about how we can improve existing monitoring. This graph shows a daily metric of one of our DynamoDB tables from midnight to 11 p.m. Let's say this metric monitors request latency. We can see that the graph tells us that the request latency was lower in the morning, but right around 8 a.m. spiked up, and then after 1 p.m. slowly lowered until around 5 p.m. where it's similar to what it was in the morning, even lower. The two vertical lines here represent thresholds, the blue one being warning threshold, which should mean that the metric is approaching state where the application could experience outage or degradation of performance. And the orange vertical line above it represents a critical threshold, which means degradation of performance and/or outage. We see from the graph that the application is not doing rather well. However, we also hear reports that only few issues were reported midday. According to the set thresholds, the application is experiencing a lot of problems for the majority of the day and night. These thresholds also potentially produce substantial amounts of alerts, which leads to responsible people silencing them or turning alerts off. What we could do is to raise these thresholds according to the new findings and reports from customers so that less false positive alerts are produced. One thing to bear in mind, the previous thresholds might have been set according to trends our application had at the time. But times change, and therefore it is important to always proactively look for monitoring improvements. Let's talk about metrics that we can use to monitor DynamoDB tables. First, let's talk about capacity monitoring metrics. With capacity metrics, we can monitor behavior of provision throughput of our base table as well as our secondary indices. For example, we can set our monitoring policy between 10 and 1000 read or write capacity units, but we would like to have an alert when the capacity approaches 500 units to perhaps investigate the cause of such high capacity. Such alarm can serve in case we want to keep the autoscaling policy to 1000 capacity units to provide our application with performance it might need, but we also want to know when these spikes occur. We can also add thresholds to when the capacity starts to approach our provision throughput limits to prevent the request throttling from happening. We can monitor two metrics in this case. There are consumed read capacity units and consumed write capacity units. We can monitor minimum, maximum, average and sum of provisioned capacity at 1-minute intervals. With these metrics, we can also monitor sample count, which serves to monitor the number of requests. We can therefore use sample count to monitor our on-demand autoscaling tables. The next group of metrics is throttling metrics. These can provide metrics such as write throttle events and read throttle events. These metrics can provide an insight into whether read or write requests are being throttled at any given time for base table capacity as well as secondary index capacity. This group of metrics also provides monitoring of throttled requests. We can set this metric to provide an insight into throttled requests separated by a specific operation. For instance, whether throttling happened during deletion or update of an item. The next group of monitoring metrics are errors. This group includes monitoring of user and system errors. User errors usually occur when an application or client uses an invalid combination of parameters, an attempt to update a non-existent table, or an incorrect request signature. System errors usually indicate an internal service error. You can contact AWS support in such cases to find out what happened. We also have other relevant metrics such as pending replication count and replication latency. These metrics are related to global tables. With pending replication count, we can have an insight into items that have been written into one replica but not the others. Replication latency monitors elapsed time between an updated item appearing in DynamoDB stream for one replica table and that item appearing in another replica in the global table. Another metric to consider is successful request latency. It can give us an insight into the elapsed time for successful requests to our tables or the number of successful requests. Another useful metric is time to live deleted item count. It provides us metrics to monitor the rate of time to live item deletions in our table. We previously learned that there are two types of monitoring, active and passive. Now let's talk about actively monitoring our tables. We can use CloudWatch alarms and CloudWatch events. These are two completely different solutions in what they are trying to accomplish. CloudWatch alarms attempt to utilize available DynamoDB metrics to deliver alerts to various endpoints. These endpoints can range from an email address to a HTTP endpoint. CloudWatch alarms use the same metrics as we've learned in previous clip. CloudWatch events, on the other hand, send system events such as table creation or table deletion events. CloudWatch events can use the same endpoints to send these notifications to. So let's see how these notifications are sent for CloudWatch alarms. Firstly, we configure an alarm with a certain threshold. When the threshold is reached, CloudWatch then sends a message to SNS topic, which we configure with endpoints. In the following demo, we'll create active monitoring for our elaborate employee table. We'll create an SNS topic with an email endpoint so that we can see some alarms. We'll also set random threshold for various metrics. In this case, we don't really care about correct thresholds. We just care about receiving the notification, so we will set the threshold low. We'll also randomly generate data in our table to trigger our alarms using a Python script. Let's have a look at some of DynamoDB metrics on the console. Click on Metrics tab. We can check majority of the most important metrics here for this table without creating any CloudWatch dashboards. What we have to do as a next step is to create an SNS topic where we'll specify which endpoints should receive alarm notifications. So in services, let's find SNS. and we can create a topic right from the overview here. Let's call this topic DynamoDB Warning. We don't need to fill any additional details, so let's just click Create Topic. And now we can go back and create another topic called DynamoDB Critical. What we have to do now is set our endpoints. In this case, our endpoint will be email, in particular my personal one. So let's click on any of the topics and create subscription. Let's set the protocol to email and specify our endpoint here. And click Create Subscription. Before confirming, however, this endpoint should receive a notification mail stating to confirm subscription to this topic. Let's click Create and wait for the email. Here is the mail. Let's click on it and confirm our subscription here. Let's do the same for our second topic. Now we have configured our notifications. Let's create our alarms. Open CloudWatch service, click on Alarms tab, and then create alarm. Now we'll select our first metric. For the purposes of this demo, we'll ignore metrics for our global table and streams. What interests us in this case is provision throughput settings. We'll find them under Table Metrics tab. Let's have a look at write capacity metric first. If you remember, we provisioned our elaborate employee table with on-demand autoscaling. Therefore, we have no control over provision throughput. However, what we can do is to monitor the number of requests using sample count. So let's choose that metric and set it up. Let's choose sample count and period of 1 minute. Period means how often will a sample be taken and be compared to our threshold. Select this metric. We'll name our alarm Write Warning Alarm and set our threshold to be, let's say, 20. And let's set the data point differently also. To avoid any false positives, let's say that we want to check 3 times, and if 2 times out of 3 is above threshold, then alarm. This means that the whole alarm process will take 2 or 3 minutes. We can set this in case our metric goes above the threshold a lot of the time, but does not really cause any issues with application unless it stays high for X amount of time. We can set how CloudWatch treats missing data. In case of this metric, we can treat it as good. Let's keep the state at alarm and set notifications to DynamoDB warning topic. Click Create Alarm. Let's create another one, but this time it will be a critical alarm. We'll set the threshold to 40 and choose our critical SNS topic. Not that it matters in this case, since the endpoints are the same, but when we design a monitoring solution for a company, the endpoints might be different in case of critical alarms. For instance, a critical alarm might be sent to a technical team rather than a warning message which is sent to support team. So let's create it. I have written a Python script, which you can find in assets of this module. The script produces random items and writes them to our DynamoDB table. So let's execute the script and wait. And here we go, our warning alarm was triggered. Let's check it out. We have the name of our alarm specified here, as well as additional details. And here is our critical. We can see that both checks went into alarm on the console. Now that we know about CloudWatch alarms, we can go through CloudWatch events. In the following demo, we'll create another SNS topic, we'll create a simple CloudWatch event trigger, then we'll create a new table as well as change our elaborate employee table, and then we'll investigate received events. First, let's create an SNS topic called Security Audit and use email as its endpoint. Confirm subscription to this topic. Now let's go to CloudWatch Events tab. Let's click Get Started. As a service name, we'll choose DynamoDB and leave the event type to all event settings. We can see event pattern preview. Here we can set different types of filters depending on which type of event we want to receive. In this case, we don't need any filters as we are trying to receive all events. Click Add Target on the right and choose SNS. We can see that a lot of target types can be specified here, but we'll go with our SNS topic. Choose Security Audit as our topic. Now this doesn't matter as all three have my personal email address as their endpoint. But in production environment, this would be necessary, as most of the time events of this type will not be received by the same people. We can also add multiple targets, for example if you wanted a Lambda function to receive and process them somehow. But our SNS topic will suffice for now. Click Configure Details. As for the name, we can call it DynamoDB Events. Keep the state enabled and create a rule. Now let's go to DynamoDB service on the console and create a random table with name as its primary key. We should receive create table event. And here it is. The format of this event is always in JSON, so they are a little difficult to read. But we can see that the event name is create table, as well as additional table details, for instance the name of the primary key that we specified. Let's experiment. Let's change our elaborate employee table. Let's add time to live attribute and call it expire. We received an update time to live notification to our mailbox. You can see that we can keep track of all DynamoDB table changes with CloudWatch events. In the following demo, we'll create a metrics dashboard with a few relevant metrics for our elaborate employee table. We'll also produce read and write traffic using our script to see how our dashboard looks with data. First, we need to decide what metrics do we want displayed on our dashboard. We can add and remove dashboard elements as we go, but it's always better to have a plan. Let's add global table metrics, base table provision capacity metrics in sample count, as well as request latency for all table operations. Let's go to Dashboards and click Create Dashboard. We'll name our dashboard Elaborate Employee Table Dashboard. Click Create Dashboard. We are presented with a window to add our first widget. Let's add a line graph. First, we'll add throughput metrics. Click on DynamoDB and then Table Metrics. We can add both read and write metrics to the same graph. Let's go to Graph Metrics tab and change statistics from average to sample count and period to 1 minute. 1 minute because it provides us with more granular data, but surely in some cases we'll need a higher period. Let's create this widget. Next widget we can add is to monitor latency for all our operations. Choose Line Graph again, and from Table Operation Metrics, choose All Request Latency Metrics and go to Graph Metrics tab again. In this case, let's choose maximum statistics, as we'll want to know what maximum latency was at the given time. Set the period to 1 minute again. Let's create this widget. Let's add another line graph. This time, we'll add some global table metrics. Let's create a widget showing replication latency metrics for all our tables in the global table. Go to Receiving Region and Table Name Metrics and choose All Replication Latency Metrics. Go to Graph Metrics again and select Maximum Statistic and 1 minute period again. Let's add this widget. Because we have enabled TTL on this table, let's add Time to Live widget also. But this time we can leave the period to 5 minutes and select SUM as a statistic. What we also need are current read and write requests to our table. We can add 2 number widgets in this case, each showing SUM for the past 5 minutes. So let's add a number widget and choose provisioned write capacity and adjust it. We'll do the same for our read capacity. We can also move these widgets around as well as resize them and rename them. Let's make it nicer to look at. And there we go. In the background, my Python script is communicating with the table, so we'll see some data soon. And there we are. This is how it looks with some data. In this module, we learned about monitoring our DynamoDB tables with CloudWatch. We learned about generic monitoring concepts and how we should approach monitoring planning. We learned about how to set up monitoring thresholds for active monitoring solutions and how to remediate broken alarms. We also went through each important DynamoDB metric. We learned about active monitoring using CloudWatch for our elaborate employee table. We created 2 alarms for our write provision throughput. We enabled a script that produced traffic to our table, triggering both warning and critical alarms. We enabled CloudWatch events, which we used to get notifications to get an insight into table modifications. We learned about passive monitoring using CloudWatch for our elaborate employee table. And lastly, we also created a CloudWatch dashboard, which we populated with data using our script. Hey, this is Stefan Roman, and in this module we'll look at handling DynamoDB objects, which means that we'll learn basic DynamoDB operations, including batch operations with AWS command line tools, as well as Python. Then we'll learn about table scanning and how improper scanning could be detrimental to read capacity throughput of our tables. We'll also go through various query operations as well as various expressions that can help us greatly when writing long queries. We'll also scan and query tables using AWS command line tools and Python. We'll also look at updating our table items unconditionally and conditionally using AWS CLI and also Python. And at the end we'll go through atomic counters and how we can use them to increment integer values. Before we are going to start this module, I just want to make sure that you have AWS command line tool installed with a configured AWS profile on your computer. We'll also need Python 3 installed with Boto 3 package used for communication with AWS API. Also, we'll need AWS user with appropriate privileges for DynamoDB. So we can jump into what we need to do with DynamoDB without any interruptions. Grant your user with all DynamoDB privileges. We briefly learned in previous lectures about certain types of item operations that we can manipulate DynamoDB items with. We have put item operation, which allows us to add non-existing items to our table. We have get item, which allows us to query or get an existing item from our table. Update item, which serves to update existing items attributes. Let's say we want to update age of one of our employees in elaborate employee table. We would use update item operation. And also we have delete item. This serves to remove items from our table. For example, if an employee leaves our workplace, we can just use delete item operation. But what if we want to get, add or delete multiple items at the same time? Well, we have batch operations for this case. Such operation can be used in cases where we need our application to use efficient parallel requests without programming such features into the application itself. Specifically, we have batch get item operation, which allows us to get up to 100 items from one or multiple tables at the same time. You might be asking, what if we want to get 20 items at the same time, but one of the items is not found? Does that mean that the whole request fails? The answer is no. If one of the requests failed, it would simply not return any data back. If all requests fail, no data will be returned, just an empty JSON document. We also have batch write item operation, with which we can either create or delete up to 25 items at the same time. One of the limitations is that we cannot update items with any batch operations. We can only get, put, or delete. Before we start looking at how to do these operations from a command line, we need to understand the structure of DynamoDB JSON formatting. It's slightly different than your standard JSON. Here is our JSON document from previous examples with attribute names and their corresponding values. If we would query the same item from DynamoDB, we would get this document back. It's exactly the same but in DynamoDB language. We have the same attribute names, and in curly brackets we have the data type of the attribute value and the value itself. As you can see, capital S stands for string and capital N stands for number or an integer. As we know from previous module, we have few more data types. List data type would be returned like so. We can see capital L, which is an identifier for list data type along with its elements. In this case, two strings identified by capital S. A map would be returned like so, with capital M as map identifier and two attributes within it. In this case, attribute name age with a value of 55 identified by capital N, and attribute name name with a value of Peter identified by capital S. When we use basic DynamoDB put, update or delete operations, we can specify return values. These values determine what is displayed or returned after a successful operation. The default return value is none, which means that DynamoDB will not return any information when an item is modified in any way. This would be a preferred approach in some cases, for example when an application writing to a table does not need any response. But for some applications such functionality is a must. Especially if we do manual operations, it's great to have some feedback as to what has happened in our table. So for put item operation, we can return all old values. This means that when we put and overwrite an item, old overwritten item is returned back. However, when we put a brand new item, the return value is ignored. For update item operations, we have quite a few return value options. First, we have all old option, which returns item as it appeared before modification. Similarly to put item operation, all old return option has no effect when the item does not exist. Then we have all new option, which returns item as it appears after the modification. If non-existent item is updated, this return value returns entire new item back. Then we have updated old option, which returns only updated attributes as they appeared before the modification. If the item is non-existent, the option does not return anything. And lastly, we have updated new option, which returns updated attributes as they appear after the modification. And for this return value, when the item does not exist, all attributes are returned as they appear after the update. And for delete item operation, we have all old return value, which returns entire item as it was before deletion. If the item does not exist, this return option does not return anything. In the following demo, we'll use all basic operations against our elaborate employee table using AWS Console, AWS command line tools, as well as Python, including get, put, update, and delete operations, as well as batch item operations. We'll also look at return value functions. We'll first look at these operations in AWS Console. Before we start anything, I've taken the privilege to populate the table with some arbitrary data using Python script from previous module. I've also taken elaborate employee table out of global table and recreated the table and secondary indices. This is so that we don't have replication attributes in our queries. This will also make our data cleaner and easier to understand. Let's start with simple operations using AWS Console. I'm sure we have done all of them before throughout this course. Let's click on items. And right here we can see few items that we can work with. Let's pick an item with partition key ID 7. Let's add a new attribute to this item and call it age and give it the value of 40, and let's click save. Now we have successfully conducted an update item operation on the console. Easy, right? In order to utilize delete item operation, let's delete this item. But before that, copy and paste it to our clipboard, we'll need it later. Let's open the item again and copy it. Click cancel and then actions and delete item. Now we have successfully conducted a delete item operation on the console. Now let's click on create item and then text editor so that we can paste the item from the clipboard. Delete existing attributes here, paste and save. And that was put item operation. Now we have tried all simple operations on the console, but what about batch operations? We can only try those via AWS command line tools or Python. So let's hop right into the AWS command line tool. I'll be doing the demos for AWS CLI in form of small bash scripts. It'll be easy and fast to edit them and execute commands. We'll also be using additional files alongside our commands when we are dealing with more complex commands. Here is an example of a command that we'll be looking at. I'll add variable names such as table name as well as index name when needed, just to keep our commands tidier and easier to understand. I'll also have AWS commands spread across multiple lines rather than in one line so they are easier to read. I'll also use another tool called JQ. It is not necessary for our commands to succeed, but the output with JQ looks nicer. So let's start. First we'll do getItem operation, which means that we need to specify table name as well as primary key. If you remember, our primary key for the base table consists of only integer ID attribute, so we don't have to worry about the sort key for now. This is our getItem command that we can use to query items based on primary key value. We'll always need table name parameter and key parameter. Key parameter value needs to be written in DynamoDB JSON, so we'll need to write it in single quotes and specify our ID attribute with a value of, let's say, 155. And now we can execute this command. And we can see that the getItem operation returned item with the name of Christine, who is an office coordinator at our company. If we use composite primary key for our table, we would need to specify the value of both partition and sort keys exactly so that the getItem operation would return us exactly one item. So let's try putItem operation. Let's have an assignment for this one. We need to add an employee named Peter who has ID of 156. The position that he'll be working at is DevOps. We'll also need a file containing DynamoDB JSON document that we'll specify as an argument. This is so that the command wouldn't be large and unclear with the item written in the command itself. So let's create a file containing necessary attributes. Then write a command with putItem operation, and instead of key argument, we'll need to write item argument and point the file to it. Like so. We'll also specify attribute return value argument all old, which should return nothing since we've been told that the ID of the new employee should be 156. So let's execute it. Now we can see that the command returned an old item that was overwritten by our put operation. This is a big problem since we effectively fired an employee. Let's try to get item 156 to make sure. We can use our previous script to do so. What we can do is to again create the previous item with ID of 156 using our putItem script and assign ID number of 157 to our new employee Peter. Let's copy previous item from command output and paste it to our JSON file and run the query with return values again. Let's call this file putItem recovery. Also change the command to point at our new file instead of the old one. Let's execute it now. We should see a new employee record in the output, which means that we have overwritten new employee record with the old one. Now we can create Peter's record again, but with an ID of 157 instead of 156. So let's change it. We should see no response from return values function this time, which means that the new record has been created and no item was overwritten. Now let's try a delete item operation. This is a simple command here. All we have to do is specify the primary key of an item we want to delete. Well, this time Pete didn't last long at our company and left after a couple of days. So let's remove his record from the table. Specify key ID with number of 157. Also, we can put a return values function with all directive to return the item that was deleted, just to make sure we deleted the right item. And now we can execute the command. And we can see that the item with ID of 157 was deleted. And as for update operations, using AWS command line tools, we'll have to wait a few extra clips since it uses a lot of parameters which could be overwhelming right now. As for batch item operations, let's look at batch get item operation first. Because we can get items from multiple tables, I've taken the privilege to recreate our simple employee table with name attribute as its partition key and age as its sort key. The command itself is not that difficult to understand. It's actually easier to write than all basic operation commands. The only thing that's different about batch commands, and the most difficult part, is to write JSON document which the command applies. In this case, we have a request item argument pointing to batchGetItems.json file. Let's open it and see how we can write it. We need to specify the top object as the table name of our table. Then object keys should specify keys that we want to get from our tables. The format of the keys is exactly the same as when we went over simple getItem command. For tables with composite primary keys, we'll have to specify the value of the sort key explicitly for each key, otherwise the command will fail. So let's write few keys that we want to get from both tables. I've purposely added the key that we deleted in previous lecture so we can see what happens. Now we can execute the command. We can see that the ID number of 157 is missing from the response. We can also see that both keys from simple employee table are here. For batch write item operation, almost the same simple command needs to be written. Request item argument needs to point to a file where we need to specify table names, write operation that we want to do, and items we want to put or delete from our table or tables. Let's have a look at the structure of the file. Similarly to batch read operations file, the file needs to have table name as its top object, then per table we have operation objects. If you remember, we can do two operations using batch write operations, put and delete. Therefore we can specify what operation for each item we want to do. We can have all delete or put operations or mix of them. And finally, in operations object, there is item object that we specify the primary key as well as additional attributes. For delete operations, we just need to specify the primary key. So let's write one item and delete another in an elaborate employee table. Let's delete the item that we read from elaborate employee table using batch get item operation previously. Let's also put an item with an ID of 100 with an attribute status with a value of batch write operation here. Let's run this command and see what happens. So now item with ID of 1363 was deleted and item with ID of 100 was created or overwritten. Let's use batch get item to see. Let's delete simple employee table query and change primary key to necessary ID values. Let's run it. Now we can see the item 100 was returned, but deleted item 1363 was not. Let's make a batch operation which we know will not return anything, just so that we can see what happens. And let's run it. We can see that an empty list was returned. So here we are looking at our first Python script. To explain what we're going to do in Python demos, we are going to repeat what we did in our AWS command line tools demo most of the time. This is so that we can imagine DynamoDB operations being done in a programming language, which can be deployed as a Lambda function, for example. We are not going to learn Python programming, however, we are going to learn how DynamoDB operations are done using Python. So just to explain the setup here, in our Python script, we have two packages imported. JSON package is only there to parse responses from DynamoDB, and Boto3 package, which is used to communicate with any AWS service on API level. But this time we'll communicate only with DynamoDB. We'll also use variable names, table name, and index name. We'll use simple Boto3 client to communicate with DynamoDB service. Then we'll execute the operation and assign the output to response object, which will get printed to terminal. Also, DynamoDB API usually responds with request metadata, which we are not exactly interested in, so I'll try to filter it out as best as I can. So first, let's try getItem operation here. As with AWS CLI, we only have to specify the primary key of an item we want to get. So in this case, item with ID number 5. So let's run the script and pipe the output through JQ so the output looks nicer. We can see that we got Arlene, who is a permanent data scientist in our company. Let's try to delete this record with a delete operation using the return values all old so that we can see what was deleted. And here we go, Arlene's record was deleted. Now let's put it back with a put operation. We can see that the item is specified here along with all its attributes. Let's run the script with return values to see whether we get any response back. what we get is a response metadata object, but our item is not in the output. This is because return values only return item metadata if the item gets overwritten. Let's run the same script again and see what we get. Now the entire item is in the output since it was overwritten by the same item again. This is consuming write capacity units regardless of the fact that it's the same item. Let's try batch get operation now. Same principle as with AWS command line tools applies here. We can specify table names, and per table names we have keys that we want to get. In this case, we want items from both simple and elaborate employee tables. What gets returned to us is a responses object with keys that we found. We can see Karen, we can see Ruth, and we can see Stephen we found from elaborate table. And also Bob, who's 33 years old, was found in simple employee table. Let's try batch write item operation now. Unlike AWS command line tools demo, we can just put two items in our elaborate employee table. We'll put item with ID 111 with status message Python batch write 1, and then item with ID number 112 with message Python batch write 2. Let's run the script. We just got response metadata back, so let's try batch get these items. I've set to get items with ID numbers 111 and 112 from elaborate employee table. Let's run it and see what we get. We can see that both items were successfully written to our table. We made some queries using put, get, and delete item operations in a demo. But what if we don't know what sort of items are stored within our table? Surely we can batch query items. What if we don't know the primary key? How would we query in that case? What if you want to keep track of how many items are stored within our table? Or what if we need to read 5,000 or 10,000 items from our table? Well, in all these cases, we can use scanning operation on our table. A scan operation reads or scans all items in a table and returns them. This includes our secondary indices. We can also filter return results with attribute filter expressions, meaning that only selected attributes are returned. And also we can limit the returned item count, which we can use if we want 1000 items out of table that has tens of thousands. Both read consistencies are supported, therefore strong and eventual consistency can be specified in our scan. Scans can become handy in certain situations. However, scanning the entire table at once consumes a huge amount of read capacity, so we have to be careful when we initiate our scans. Scan can potentially hinder performance of our application by consuming all read capacity. If we really have to scan during peak times, we can use pagination feature that pauses between each request. Let's say that we have 1000 items in our table and we set our pagination to 100. DynamoDB will get 100 items, then create another request to get another 100, and then again until all 1000 items are read. If we have a business critical table and we don't want to hinder performance with necessary scan, we can create a new table from backup and utilize that for scanning. These are called shadow tables. If we have a table with provisioned capacity, it is important to know that the way and frequency we conduct our queries and scanning on the table can significantly impact read capacity. For instance, let's say that the horizontal line here represents time. Here are scan requests over time. The size of the dot on the line represents how big our read operation was. Well, if we conduct scan queries randomly, all read capacity might be quickly consumed for short periods of time, without leaving any capacity for requests from business-critical applications or customers. This can lead to request throttling. To avoid this, here is a better approach to conducting heavy reading operations on our tables. With smaller but evenly distributed scan operations, we can avoid such issues. In this demo, we'll conduct scanning operations against elaborate employee table using console, AWS CLI, and Python. We'll also use pagination feature, which we'll use with the debug feature to observe how pagination works under the hood. We'll also look at how much of provisioned capacity our scans consume. We'll first do a scanning operation using a console. I've taken the privilege to create another index called scan index for our elaborate employee table. The index has ID attribute as its primary key, Also, I have added only one projected attribute to this index, and that's name attribute. This is so that we can have some variety when scanning. AWS does an automatic scan operation of items when we open the tab with items. It gives us random 100 items in selected table. We can also force scan query against the base table or any other indices here. Let's scan index. Here we have only two projected attributes, ID being the primary key and name being the custom projected attribute. Let's see how we can do these operations using AWS command line tools. Command line gives us a lot more options when we're doing scans, for instance limiting and filtering. The command itself is pretty simple. It only takes one argument and does the table name. First, let's scan our base table with no additional arguments. As you can see, we have an extremely large output. We can also see that we have 10,001 items in our table. All of them return to our terminal window right here. Effectively, whole table database is right at our terminal now. We are not exactly sure about read capacity this scan has consumed. We can see that the consumed capacity attribute is set to null value. We can therefore specify a return consumed capacity argument to give us that visibility. With this argument, we can see consumed table capacity as well as index capacity. Let's try it with index capacity and scan the table again. We can see we consumed 87 capacity units for this scan on the base table itself, but no indices are here. Let's scan index and see what the output is. We can see that scanning our scan index consumed 19.5 capacity units. This is because we have only two projected attributes instead of all, which greatly reduces the size of the index. We can also see that zero read capacity was consumed on our base table, since the base table was not touched during this scan. But what if we don't want to dump the entire table to our terminal? What if we just want few items without consuming so much read capacity? We can use limit argument and specify how many items we want back. We can scan the secondary index again. Let's add the limit argument and run the command. Let's say we want 10 items back. We can see that only half of read capacity unit was consumed in this case. So limit argument helps us greatly when we don't want to scan the whole table. What if we need to scan the whole table and we are worried about hindering performance? We can add pagination argument in this case. Because we have 10,000 items in this table and the index, let's split the request into 10 pages. Therefore, we need to set the page size to 1000. Let's add the argument and run the command. We can see that nothing changed here. It behaves like a normal request. However, we can see that read capacity units are greatly decreased. To see why this is, we can gain more visibility by specifying debug argument, which will show us that multiple requests were made. I'll also remove standard output from this command so that we can see the requests being made better. Let's run the command again. Let's scroll all the way up. We can see the first request was made and returned 1000 items. And immediately another request was made which returned another 1000 items. And again, and again. Let's try this without pagination. Let's scroll up. We can see that only one request was made with the return value of every item in our secondary index. So let's try something similar in Python code. Let's do a scan on the whole table first to see if we get similar results. We are now interested in consumed capacity, so we can set our JSON Python filter accordingly. Let's also have returned consumed capacity set to indexes value. Let's scan the base table now. We can see that we get 87 consumed read capacity units. Let's change the script to scan our scanned index. If we repeat the request on our scan index, we should get the same number, which I believe was 19.5 units. We can see that the value of consumed read capacity units matches. Therefore, it does not really matter which interface you're scanning with, it will always consume the same capacity units based on items stored within the table or the index. We've talked about scanning and how we can use it to read all items from our table. But what about specific item ranges? We explored getItem operation, which read and returned a specific item to us. But what about if we want a range of items? We can use query operation, which queries items from base table as well as secondary indices. To give you an example how a query might be used, let's say that from our elaborate employee table's secondary index, we want to get all items that have certain date accessed value, but we are not sure about the name of the employee who accessed our building. We could use query operation to obtain all records without specifying explicitly what the sort key is. Query operation uses primary key of a base table or a secondary index to query data. And you can also set read consistency to either strong or eventual. So let's talk about how we can use key condition expressions to make our queries more precise. It is important to mention that partition keys always have to equal a value. Therefore, for partition keys, we always have to use equal condition. However, we can also use equal condition for sort keys. For sort keys, we can also use less than, where the value of the sort key is less than the value that we specify. We can also use less than or equal to, more than or equal to, between condition, which can be used for integer sort keys, where we can set a range of integers and our query operation would return anything in between. For instance, we could query a partition key with a Bob value, and our sort key age could be between 20 and 30. The query would return all Bob's records aged between 20 and 30. The last condition expression is a little different. Begins with condition can evaluate whether attribute value begins with a substring. For instance, get all items where partition key equals a certain date and our sort key can begin with a capital B. We can use such query if we are not sure what the string actually is, but we know how it begins. We can also use this to perhaps query alphabetically. Before we go and make some queries, we need to know a few expressions to help us with readability of our requests and responses. First of all, we have expression attribute name. We can use this as a placeholder to replace actual attribute name with an alias in all our queries. But why would we do that? Well, some attributes might have really long names, so it's always nice to shorten them when writing a command line query. Another reason is that some words are reserved in DynamoDB world. If we have a reserved word as a name of our attribute or a key, we cannot query directly, but we have to use attribute name expression to, let's say, mask its real name. We have few of these reserved words in our elaborate employee table, such as ID, name, or even position attribute names are reserved and cannot be queried directly. Another expression that we can use is expression attribute value. Similarly to expression attribute name, this expression serves as a placeholder for attribute values themselves. Let's say that we want to query attribute values using DynamoDB JSON. Expression attribute values can help us with assembling such commands so we don't have to escape strings or quotes, which can get very messy when writing complex queries. Another expression that we can use to help us out with understandable output is projection expression. These are utilized to filter attributes returned to us. For instance, if we want to make a query that return only name and age attributes. In this demo, we'll conduct query operations against elaborate employee table as well as their secondary indices using AWS console, AWS command line tools, and Python. We'll also use use key condition expressions to define our query, expression attribute values, expression attribute names, projection expressions, and lastly, we'll use filter expressions. First of all, we'll conduct query operations using AWS console. Base table query operation in this case would be exactly the same as get item operation, since the base table only has a simple primary key with ID attribute being the only attribute we can query. So we won't repeat that. Let's have an assignment for this one. Let's find a person to promote from an intern position to permanent position in our DevOps department. Let's choose an index with the composite primary key. Let's find the person who recently visited our building. So a good candidate for searching would be our Access Application Index, which has a primary key consisting of last access date as well as name attributes. From the drop-down menu, also choose Query. For the date, let's pick 10th of June 2019 and click Start Search. We can see quite a few items here. Let's refine them using filter expressions. Let's add a filter that will filter out based on position DevOps. And another filter that will filter out based on contract type intern. Let's click Start Search again. We get few people eligible for promotion here, but let's pick only one. Let's pick someone whose name begins with a capital G. We can use the sort key for that purpose. Let's add begins with search with a substring capital G. This is also our key condition expression. Let's click Start Search. We can see that one candidate, Gloria, was returned. We can immediately promote her to a permanent DevOps position. Let's try querying with AWS command line tools. Let's say that for the purposes of this demo, we are trying to make a statistic of how many permanent employees work for each department that have accessed our workplace building at a certain date. We'll use position application index for this one, since it has position attribute as a partition key and contract type as its sort key. So let's write our condition expression for this one. Our first position can be HR. We can see a few problems here. Key condition expression argument takes only string as a value. This means that we cannot use these map objects within the key condition expression. What we can do is we can use expression attribute values in this case. We can assign a key value to the attribute value we are trying to find. Like so. We assign :PV to position value and :CTV to contract type value. Think of these as variables in our queries. Now we can reference these keys in our condition expression like so. Let's run the query and see what happens. We received an error stating that position attribute name is a reserved word. Therefore, we are not able to query directly. What we can do in this case, we can use expression attribute names to mask the name of the attribute. They look almost exactly the same as expression attribute values, except instead of colon, we use hash in front of them. We can add both of the attribute names even though contract type is not a reserved word. Let's reference them in the key condition expression and run the query again. We can see that the query ran successfully and returned 589 results. Just to mention that we can assign any name to expression attribute values and names. It's always best to find the balance between short and understandable names. But now that we have a working query, we can filter results even further. Let's use filter expressions to filter these results by last access date. Just to keep it identical, let's create expression attribute name and shorten the name of last access attribute, and also create a new expression attribute value, and let's say we want 12th of June 2019. Let's add a filter expression now. Because we need to find people based on position, contract type, and the date they access our workplace, we have to use equal filter. Let's run the query now. We can see that only 21 records are returned. But right below we see that 589 items were scanned. This means that the query consumed read capacity for all 589 items, but then our filter expression reduced the number to 21. This means that the filter expressions work after the query is executed, and not with it. We can see that the returned items are there with all attributes. Because we built a query based on these attributes, we most likely already know them beforehand and do not need it returned to us again. We can therefore use expression projection to refine the results even further. Let's say that we just want name and ID attributes since we haven't queried for those. Let's add two more expression attribute names for ID and name. And add projection expression argument. And let's run the command again. We can now see that we have refined results. We can also see that our command is rather messy at this point. It is difficult to distinguish especially expression attribute names. What we can do is to remove them from the command itself and add expression attribute names and values to files and then point the arguments to the files. Like so. So in the previous demo, we've learned about expression attribute values and names. We've also learned about projection and filter expressions, so we'll not go through that again. What I'll show you is how I can write queries using all of these expressions in Python. Let's say that our company runs a lottery where they need few people who are the first employees of our company. So these people will probably have low ID numbers. Next prerequisite is that people who are eligible are people who access their workplace on a particular day. Let's say 12th of July 2019. And also another prerequisite is that their names need to start with a random letter, let's say capital B in this case. We also need names of people returned to us, so we can use projection expressions. Let's start by building our query here. Because we have to query people based on the last access attribute, we can use access application index, which has last access as partition key, and also name attribute as sort key, so we can use that for the name prerequisite. Let's start by adding expression attribute names. Here we have last access as LA, name as N, and ID as I. Let's add our values. We'll need 3 for this case, 1 for the date, 1 for the ID number value, and the last one for the letter capital B. So LAV stands for last access value, IV stands for ID value, and NV stands for name value. We've set ID value to 150 since we'll only query people with low ID numbers. Let's write our key condition expression now. And also we'll need to refine these results by name attribute beginning with capital B. For the filter expression, we can write where ID attribute is less than 150, which will essentially give us what we are looking for. Let's write projection expression also to filter out attributes that we don't need. Now we can execute the query. We can see that one employee named Benjamin won the company lottery. Congratulations, Benjamin! So far throughout this course, we have been conducting DynamoDB operations against simple items. We have before learned that DynamoDB supports lists and maps as data types. For example, take this item with ID of 100. We have prices map data type with various nested attributes. But how do we get to them if we only want to receive price for bed? We can construct our query like so. We can use operation getItem to get item with ID of 100, and then we can use projection expressions along with the reference operators to specify that our attribute is embedded within another attribute. For maps, we can use the dot as the dereference operator to specify that in map prices we want bed. The query would effectively return only the price of bed and would not return other attributes in the price map. What about something more complicated? Let's say that we have the same item with ID of 100, but now bedroom map is nested within prices list. So effectively, this schema is ready to have multiple rooms as maps inside prices list, with prices of each thing belonging to room type. But how do we get to our bed price this time? We can use getItem operation again to get item with ID of 100, then we can use projection expression again alongside different dereference operators to specify that our attribute is embedded within a list at a certain index position. It's 0 in this case, as it's the first element in the list. Then, as in our previous example, we can specify path to the price of the bed, which is nested in bedroom map. In this demo, we'll update few items in elaborate employee table using AWS command line tools and Python. We'll also use update expressions that will help us specify what items need to be updated and how. We'll also look at nested attributes and how we can update items with them. Before we start, let's go through some of the files here. As you can see that for almost every argument we are using a file. This is so that the command is clear enough to understand. We have our key file, which pretty much just specifies the key with ID of 100 that we are going to work with in this demo. Then we have expression names file, which holds expression names that we'll work with. And lastly, we have expression values file, which holds all values that we'll use in this demo. So let's start. If you remember in the previous demo, we created a single person and updated an attribute from intern to permanent through the AWS console. This time, we'll do the same by using a command line. Let's first query the person with ID number 100. We can see that her name is Sandra. She is a developer and is an intern at our company. We'll promote her now. Let's write an update expression. The expression means that we want to update or set attribute name #CT, which points to contract type attribute name in our file, to :CTV or contract type value, which is set in our file to string value of permanent. Let's run the command with return values of updated new. This should return us only attributes newly assigned values. We can see that the contract type was now set to permanent. Let's do something more complex. Our company has implemented a new policy where every employee needs to have at least 3 previous addresses as well as names of all kids that they have in the records. The addresses need to be under addresses attribute name and kids' names need to be under kids attribute name. We can update Sandra's record first. Let's change our expression names here. Now let's change values file. We can see that key :A points to a list data type containing maps of previous addresses. Each of the maps has street, number, and country attributes set to random values. We can also see here at the bottom that key :K points to a list full of kids' names. Let's set our update expression now. We need to set #ADS to :A value and #KDS to :K value. Let's run the query now, but this time without return values. Now let's query this item. We can see that both of the attributes were added to the item. But now let's make a query only for the first address. Let's use projection expression to do so. Let's add addresses attribute with 0 index value, which should return us the first address in the list. And there we go. But what if we want to return a specific street name? We can use the reference operator here and add street attribute name after it. And here we go. Only the street name of the first address was returned. Now let's see how we can update items in Python. We'll do something different this time. Let's say that our HR department wants to promote 9 people to a permanent position and they gave us 9 ID numbers to promote. These people are mostly contractors and interns. Because we don't like wasting time, we can do all of them in one go using Python. So let's explain the setup here. We have our ID numbers provided to us by the HR department. This is what's different right here. We have a loop that loops through every one of these IDs and runs the following update operation against it. We can see that here we have a format function which pretty much just fills the curly brackets with the appropriate ID value. We have expression attribute value CTV, which is set to permanent. This value will be used over and over for every single one of our ID numbers. And also we have expression attribute name CT, which points to contract type attribute. We also have return values set to updated old, which will give us values of attributes before modification. In this case, we are updating only one attribute, and that's contract type. So only one attribute per item should be returned. Let's run the script and see what happens. We can see that 9 values were returned. We've just promoted 9 people in seconds. So we learned about various write operations in this module so far. By none of the cases, when we wrote a new item or updated an existing item, we never specified whether the item itself could be updated or overwritten. DynamoDB write operations do not check conditions by default. Therefore, they are all unconditional operations. When we, for instance, put an item into our table with the same primary key as our existing item in the table, the existing item gets overwritten with no warning or prompts. Also, we might want to update an item if certain criteria are met for that item in some cases. DynamoDB has functions that might help us with such issues. They are called condition expressions. And unlike key condition expressions, which can only evaluate primary key attributes, condition expressions can evaluate all attributes in our items, even nested ones. Such expressions can prevent accidental modification or deletion of our items. This can be crucial when dealing with production data. Also, condition expressions assure idempotency, which means that repeated write operation will not change the outcome. To explain how condition expressions can help us, let's describe this scenario. Let's say that Emma wants to increment the price of attribute on an item with ID of 1 by 4, but only update price if the value of price attribute equals to 20. When the query gets to DynamoDB, the Emma's condition expression, which is to increment only if price equals to 20, gets evaluated. And in this case, the update query applies the increment. But what if at the same time Rebecca wanted to update the same item by increment by 5 this time? Well, she would construct the same query which says to increment price by 5 if price equals to 20. When she sends the query to DynamoDB, the condition expression gets evaluated, and unfortunately for Rebecca, it returns false, and so the item does not get incremented this time. If they did not use condition expressions, the price would now be 29. Condition expressions might not be needed when counting the number of visitors on our website, but they would be necessary in applications where we need to keep exact count without allowing duplicates. Alongside basic comparison operators that we discussed, we can use functions such as attribute exists, with which we can only execute write operation if an attribute exists. Attribute not exists, which does exactly the opposite and executes write only when the attribute does not exist. This function is particularly useful when putting new items in our table. We can, for example, check for existence of our primary key and not write when the key exists already, which can prevent loss of data. We can use size function, which checks for attribute value size. We can use begins with and check whether the attribute value begins with a substring, the same as with key condition expressions. We can also use attribute type function, where we can check for the data type of a particular attribute, and contains, which evaluates whether the attribute value contains a substring. In this demo, we'll utilize putItem and updateItem write functions to update our elaborate employee table conditionally, using only AWS command line tools this time. In the demo, we'll also explore and utilize conditional functions. So just to explain the setup here, we have a file with the item we want to have in our table. The file contains an item with partition key ID with a value of 10, including a map attribute type address with 3 other attributes embedded within it. Let's put this item so that we are sure it exists in our table. We can set our first condition expression right now. We have another item in another file with the same ID number of 10, but this time it's a completely different person. We'll try to put this item with a simple condition expression. The expression will check whether the attribute ID value already exists in our table. We'll also point the command at a new item file. We can also add a return value to see if the item was overwritten if the command successfully completes. Let's execute the command now. We get an error saying that the conditional request failed. Let's do something more complex. Let's say that our company has a new policy where employees need to have an emergency contact in case of an emergency. This applies to only permanent employees and for employees who have addresses street in their record. Also, we don't want to overwrite any emergency numbers that are already present to ensure true idempotency. So let's start looking at our values file first. We'll need an emergency number value. Let's call it ECN for emergency contact number. Because this will apply to only permanent employees, we'll need to add another value for the contract type. Let's call this one CTV for contract type value and set the value to permanent. We'll also need few attribute names for our conditional checks. First, we need the emergency contact attribute name. Let's call it EC for emergency contact. We'll also need contract type. Let's call this one CT. We'll need a couple of more, since we need to get to address and then street attribute embedded within it. Now let's add update expression to our command, which is quite simple. Set emergency contact to emergency contact value. Now for the condition expression, we need to check whether attribute emergency number exists, and if so, do not update. We'll need another one stating that only update if contract type is equal to permanent. Then we'll need to check whether embedded street attribute exists. Let's write them all. For the address map object, we can just use the reference operator like so. Let's run the query with return values set to updated new so that we can see whether our attribute was added to the item. Also, let's point the expression attribute names to a correct file. Let's execute the command now. We can see that the emergency number was added to the item. Now let's run the same command again and see what happens. The command failed due to emergency number being already present. We learned about updating our items independently without having to worry about executing the same request multiple times. But what about if we just want to increment our value each time there is a request to our table? We can use atomic counters, which simply increment values. Atomic counters are not idempotent, which means that each request to the table will increment the value. They are used in applications where accuracy does not matter very much. A few applications this would be useful would be increasing price of a product for our website visitors, who always visit the product page, which means that they are interested, but they are not sure about buying. When the price increases, they could be forced to buy the product due to ever-increasing price. In this demo, we'll look at atomic counters and increment value on elaborate employee table using AWS command line tools and Python. So first, we'll do this in AWS command line tools. Let's say that our company said that we need to track how many times our employees access the workplace building. We are tracking when they accessed, but we are not sure how many times. So let's create a new attribute called countAccessed and set the value to 0. We can use item ID number 20 this time. We'll run it with return values, so we'll get to see what was updated. We can see that the return value states that countAccessed attribute was set to 0. Now in order to update this value, we'll need to change the update expression a little bit. What this expression says is that we want to set countAccessed to countAccessed plus the value that we specify. But now it's always going to increment by 0, so let's change the value to 1. Let's execute the command now. We can see that the countAccessed value is now set to 1. Let's execute the script a few more times. We can see that the value always increments by 1. Now let's change the increment size to 5 and execute the command a few times again. We can see that the value of countAccessed increments by the set value. So again, we can do the same for item number 30 in Python. First, we'll create a new attribute for item ID with number 30. Then we can change the update expression to increment as we did with AWS command line tools. Also, we have to change the value from 0 to value that we can increment with. Let's run the script a few times now to see what happens. We can see that the value increments as in previous example. So in this module, we learned about basic DynamoDB operations and how we can use them to put, get, or update items in our table. We also went through batch operations where we fetched, updated, and deleted items from a couple of tables at the same time using AWS command line tools and Python. We've scanned our elaborate employee table as well as its secondary index, where we compared consumed capacity and how we can reduce consume read capacity by using pagination feature. We've also learned how to query from DynamoDB using various expressions using AWS CLI and Python. We've also learned how to reference all expressions to a file to make our commands easier to understand. We've also learned about modifying our items unconditionally and conditionally in AWS CLI and Python. This is where we explored condition expressions and their functions which we use to make our writes idempotent. And at the end, we learned about atomic counters and how we can use them to increase values with every update request to our table.